Today, on how it's made. Magnets will reveal the secrets of their attraction. Cooked ham. The pig's short-shanked redemption. Silver-plated teapots. Spouting niceties. And crash test dummies. It's safe to say they're a smash. Magnets attract to certain metals and each other. That's handy for more than sticking stuff to the fridge. They help run motors and generators, among other things. Magnets occur in nature, but 2 centuries ago, people figured out how to make them using electricity. You could say it was a take-charge situation. You can't see or feel the force causing this globe to levitate, but it's not magic, it's magnetic. To make magnets, they must first create a sand mold of the magnet shapes. They load this pattern of 4 magnet shapes into a machine that fills it with sand. They remove the pattern and smooth the surface, dimpled by the machine's lid. Then it's back inside, but this time, the machine pumps in gases to chemically harden the sand. It takes just seconds to solidify. They lift out the sand slab, revealing the impression of the magnet pattern. It's now a mold. Magnets come in many shapes and sizes, as do their molds. Now they're ready to mold the magnet shapes. They take copper, cobalt, sulfur, nickel, pure iron, aluminum, and titanium. They load all these metals into an electrical induction furnace. It generates a pulsating electromagnetic field that heats to more than 1600 degrees Celsius, melting everything into a molten soup. They pour it into the sand molds. The molds burst into flames because the gases that harden the sand are highly flammable. They slide the blazing molds to another part of the foundry and knock them to the floor. Then they bust them open with a sledgehammer to get air inside so they cool down and the gases burn off. They shovel everything into a bin and sort the metal shapes from the sand chunks using, what else? A magnet. The molded pieces react like ordinary metal. They don't yet have magnetic power. Some are shaped like rings. Threaded onto a copper pipe, they'll be used in electric motors. They place the ring-covered pipe in a much larger tube. Then they center it by packing silica sand tightly around it. The sand will hold the rings in position during the next step. They seal both ends with concrete, allowing the inner copper tube to protrude slightly. Then it's into another electrical furnace. It heats the tube full of magnet shapes until it's red hot. This primes them to accept an electromagnetic field, which will be delivered by this metal rod. They slide it down the center of the copper pipe and clamp it in place. Water keeps the pipe from melting as they deliver a low-voltage, high-current charge in a cylindrical formation, important for motor magnets. They break open the seal. The process has left the ring shapes mildly magnetized, but most importantly, it's oriented the magnetic field properly. They grind away any rough edges. At this point, all magnets are pretty useless. But this machine will empower them. It delivers an electromagnetic charge to the metal, which magnetizes it. The establishment of that weak magnetic field earlier has laid the groundwork for this moment, ensuring that the magnetization is properly oriented. Now that's some serious magnetic muscle. In their various forms, magnets continue to exert a lot of pull in our society because their invisible power helps keep so many things running. Ham is the hind leg of a pig. You can buy it raw or roast it yourself. Or you can buy it already cured and smoked. You can buy your ham boneless or with the bone still intact. Bone-in ham has more flavor because processing doesn't disturb the natural muscle, fat, and bones. Thousands of hams arrive at the factory, fresh from the slaughterhouse. The factory's automated sorting system weighs each ham, then knocks it into the designated vat. By grouping hams of similar size together, the factory can better control the quality of the curing and cooking process. Each vat empties into a tumbler. The machine spins the hams for about 5 minutes, loosening the skin from the meat. Tumbling makes this next step easier. Using specialized trimming tools, workers cut off the skin. They use an automatic trimming machine to skin the back portion, called the butt. In keeping with traditional style, the machine leaves just a small amount of skin on the thin part of the leg, called the shank. Now the circular wizard knife does its magic. They run it across the butt to remove all but a centimeter of fat. Finally, they chop off the base of the almost meatless shank, called the hock. Other workers prepare the curing solution: water, sugar, salt, and other ingredients that are a company secret. This recipe produces that trademark ham flavor and pink color. Without it, the meat would come out tasting like a pork roast. Pipes feed the solution to an injection machine that's equipped with 138 needles. As the hams pass underneath, the needles inject curing solution. This ensures the cure penetrates thoroughly and evenly. All that piercing also tenderizes the meat. Next, workers load a machine called the stuffing horn. Like a cannon, it fires each ham into a heat-resistant cotton net. Workers close each one with an aluminum clip, then cut off the excess. Cooking hams on trays would flatten the underside, so workers hang them by the nets to keep them nice and round. They move the cooking racks into a food processing oven, the industrial equivalent of a traditional smokehouse. They pour hickory wood chips into the oven's smoker and start her up. For the next 12 hours, the hams slow cook at temperatures ranging between 65 and 82 degrees Celsius. This tenderizes the meat and gives the smoke ample time to seep in. After cooking, workers shower the hams in cold water for 10 minutes. This rinses away drippings falling from higher hams onto lower ones. Then it's on to the chill area, where over the next 36 hours, the hams cool to -2 degrees Celsius. The nets come off and packaging begins. The factory sells hams whole or, using a bandsaw, slices them into halves or smaller sizes, such as single-portion ham steaks. Workers position a soft plastic pad over the bone, then bag the ham in plastic. The pad prevents the bone's sharp edges from ripping the package and destroying the airtight seal. They position each bag for vacuum sealing. From there, it's all automated. A vacuum chamber descends over each bag, sucking out the air and sealing the plastic. A robotic arm transfers the vacuum-sealed ham to a conveyor belt, leading to a hot water bath. Each bag spends a mere 5 seconds in hot water, but that's enough to shrink the plastic tightly around the ham. Refrigerated, the ham stays fresh in its airtight package for 3 months. Store it in your freezer, and you can ham it up for 6 months more. Teapots. The Mayans started using them 2,600 years ago, probably for hot chocolate. Their evolution spans several hundred years, and they come in a wide range of styles. More than just vessels for brewing and drinking, aficionados consider them essential for that perfect cup of tea. These silver-plated teapots come in every style imaginable, and making them requires the talent and skill of an old-world master. A century-old hand-circling machine cuts a perfect circle out of a brass sheet that's 1.5 millimeters thick. They shape that brass disc, first with a forming die mounted inside a press. After lubricating the press surface with vegetable oil, they position the disc on the press, then cover it with a polyurethane stopper. As the press applies 3 tons of pressure, the die moves upward, shaping the disc from underneath. The stopper provides counter-pressure to keep the die from breaking through the brass that thins as it stretches. They call this preliminary shape the draft shape. They insert the draft shape into another die and repeat the forming process to produce the final shape of the teapot's base. Next, they solder on the teapot rim, which was made the same way. A craftsman then hammers the metal to remove any imperfections left by the pressings, and punches in the maker's mark. Spinning is another technique they use to shape metal teapot parts. Here, a craftsman uses a tool to shape a copper teapot mounted on a lathe. They decorate the metal using a technique called hand chasing. With a paper stencil, he applies the design in white powder. He pencil traces the pattern, then hammers in the design with a variety of tools. This intricate process requires the talented hands of an expert artisan. For the teapot spout, workers press brass plates into left and right side dies. Once again, they use 1.5 millimeter thick brass and drop a 1/4 ton press to produce the final spout shape. To assemble the spout, they brush on soldering paste, wire the 2 halves together, then fire the spout to 370 degrees Celsius. The spout gets an acid bath to remove all the impurities the soldering process left behind. Using pumice, which is crushed volcanic rock, workers polish the teapot with 3 progressively finer grades. They give it one final buffing to ensure the surface is perfectly smooth. With diamond-tipped hand tools, engravers can etch additional features. Everything from custom designs to company logos. Workers now screw on the lid, wire up the teapot, and immerse it in cleaning chemicals, then in a silver plating bath. Just before shipping, Workers attach hardware and perform a final cleaning. Finally, shippers wrap the teapots in acid-free cellulose that prevents the silver from tarnishing. It takes a talented team of highly skilled craftspeople to create these unique teapot designs, in styles ranging from Elizabethan to ultra-modern. Crash test dummies come in all shapes and sizes. They may look human, but they're actually guinea pigs for a wide range of impact tests. How do they make dummies whose form and structure mimic the human body? Here's our version of Crash Test Dummies for Dummies. Crash test dummies are designed to take some serious hits. Automakers use the crash data that they provide to build safer cars, vans, and trucks. A dummy's anatomy is pretty simple. There's a metal skeleton made of steel and aluminum bones. Those bones contain load cells, electronic devices that measure crash force. On the outside, the dummy's skin consists of a vinyl covering. To make the load cells, a milling machine shapes steel bars using a solid carbide end mill. Lubricant cools the intense heat and washes away the metal particles. Using a precision tool called a dial indicator, they verify the load cell's dimensions to within 5/100ths of a millimeter. They install the strain gauge, the component within the load cell that measures crash force. The hair width wires that connect the strain gauges are so delicate that soldering them requires a microscope. The vertebra in the dummy's neck also contains a load cell. The strain gauge they solder inside it measures not just lateral and vertical forces, but also twist or torsional force. Now they lay out the bones and corresponding load cells that will be connected to the dummy's rib cage. To make the rib cage, steel bands are bonded to a flexible damping material. This material was originally designed to deaden sound in nuclear submarines. In a test crash, these dummy ribs compress the same way human ribs do. A technician bolts the entire rib assembly to the spinal column and covers it with a plastic chest plate called a bib. The long bones and load cell forms are inserted into aluminum molds. Then workers bolt the molds shut and pour in liquid vinyl. The molds bake at 170 degrees Celsius for 10 to 20 minutes. When they come out, the first step is to cut away flash, the excess vinyl that oozed out of the mold during the baking process. Then a technician visually inspects the components to ensure an accurate fit. This is no ordinary vinyl. It's specially designed to resemble human flesh in consistency and density. This gives researchers realistic crash data. Now they install the bones, starting with this tibia, into their respective vinyl compartments. Zippers allow the engineers to remove the components easily after performing a crash test. A technician bolts all the dummy joints in place and ensures they have a human-like range of motion. Using a neck compression tool, a technician lines up a load sensor with the neck vertebra and fastens the completed neck assembly to the dummy head. Next up is the dummy's upper body. He bolts the thorax onto the pelvis, the head and neck assembly onto the thorax, then fits a vinyl jacket over the chest. Finally, he bolts on the limbs, containing all of those long bones and load sensors. Crash test dummies range in size from newborns all the way up to 102-kilogram adults. This enables researchers to be sure that seatbelts and airbags protect everyone equally well. It took a full 12 weeks to make this dummy, and now he's ready for a life of hard knocks to make traveling safer for all of us.